Okay, welcome everyone to the October 26, 2021 Open Planetary Lunch. I'm Chase. My lunch today is some lemon lime flavored seltzer water. Our speaker is Csm Mapel from USGS on using the community sensor model standard with planetary data. Thank you for being here, Jesse. Thank you for volunteering to give a talk. And when you're ready, you can take over screen share and begin.
Hi, thanks for having me, Chase. Glad to be here. Should be able to see my slides now. Beautiful blank gray title slide. So as Chase said, I'm a software developer at the USGS Astrogeology Science Center. I work primarily with the ISA software package, but in the last couple of years, I've been working a lot more on our work to support the community sensor model standard, particularly getting that from a terrestrial-based standard and adapting it to work with planetary data. So I'll be talking about the work we've been doing on that over the last about 5 years, and then also talk about some of the work that's been going on in the community and kind of where we want to go, along with a brief demo towards the end. So first of all, everybody can probably see my screen share, so let's hide that. The standard is a sensor model standard, and that means that it is responsible for taking coordinates in image space and translating them into coordinates in ground space and vice versa. And along that transformation process, we want to make sure that we have rigorous error estimates and error propagation so that we have good uncertainties and error modeling all the way through that. It's a very generic standard, so it supports everything from video to LiDAR to framing instruments to push broom instruments to whisk broom instruments. It supports all sorts of stuff. Unlike for example, ISIS, it is both Unix and Windows supporting, so it's works on the 3 major platforms really of Linux, OS X, and Windows. And the platform comes from the US government. The National Geospatial Intelligence Agency, NGA, is responsible for it. It's also used heavily in the DoD. So this was a terrestrial standard that's been used a lot for US government intelligence and such data collection. With, I believe 3.0, they've kind of changed it from the tactical sensor model to the community sensor model and kind of pushed it out there. And we're starting to see more promotion of it as a more just generic, high quality tested sensor model standard. So this is kind of pushing out of the government intelligence realm and more into some of the more open spaces, such as planetary data. So you can find the code for it on GitHub at this address. We also have a mirror on the USGS Astrogeology GitHub that has a CMake build system added to it if you're interested in that. And the documentation is a little hard to find. If you just Google it, you'll probably get old docs. So I've put the link to the actual full documentation here. So the standard itself is a C++ API, really at its barest. There is a very small library component to it that is compiled, but it's primarily a lot of helper functions and stuff. The real heart of the standard is the API for the models. So kind of the big parts of the API are the models. This is your sensor model that does the transformations I've talked about in the error propagation. It takes adjustments, it gives you a little bit of information. The image support data, or the ISD is what I'll be calling it, that is basically the initial data you need to build your model. So in a lot of planetary stuff, the ISD will contain things such as your ephemeris data from spice kernels. It'll contain things such as your maybe the capturing mode from the imaging label. So stuff like binning, TDI, things like that. Next, we have our model state, which is similar to the ISD, But the ISD is what you make a model out of. The model state is that model serialized. And so on the next slide, I'll show you kind of a nice little flow of what this looks like. But the model state is really what we'll be working with. You're going to go ISD to model. And then after you go to that model, you're going to bounce back and forth between your model state and your model. And all of this is mediated by a plugin. It's slightly confusing. There's a plugin singleton that is responsible for basically making and registering the different models. So here's the confusing part. It is a plugin architecture for the standard. And so we have these plugin libraries, which are just dynamically loaded libraries, and they will usually contain one plugin and a handful of models. So like I said, again, here's kind of what the flow will look like. Your plugin library will have a plugin and some models. The ISD is defined as part of the standard, and the model state is actually just a raw string. But the format of that model state is up to the plugin library. It's opaque to the user. So it's that's why I've kind of lumped it in there. And so you have your ISD go to the plugin gives you a model from that ISD. Your model can then be serialized to a state, and then you can use the plugin to regenerate your model along with any changes or adjustments you've made to that model at a future point. So what isn't a part of the CSM standard? Well, everything that isn't a part of the CSM standard basically falls to what we call sets or sensor exploitation tools. And this is effectively anything that calls the CSM API. And some of the big things that's responsible for are data IO. So, opening things, closing things, making HTTP requests and stuff. All of that is the responsibility of the set. The set is also responsible for modeling the surface. So the CSM standard does not have anything to do with how your surface is modeled. What the CSM standard gives you is this locus, which you can see the picture of on the right. And what that is effectively is that for an imaging coordinate, the imaging locus is the set of body coordinates that that image coordinate could relate to. So in a very basic pinhole camera, this is effectively your line of sight vector. But in this picture here, you can see we have like some atmospheric diffraction going on. So the locus is curved. For a SAR instrument, your locus will be like a ring around the antenna because it is everything at a consistent range effectively, at least in range-based SAR images. The other thing the setter is responsible for is pixel values. The CSM standard does not describe anything to do with pixel values and stuff. Realistically, in most modern software, that's going to be like the realm of GDAL and stuff. So the CSM standard is very much heavily focused around, transformations of these imaging and body coordinates. Other stuff that's not in the CSM standard opposed to other sensor model standards, such as the ISIS sensor model or the CAVOR sensor model or the CAVOR-A sensor model, is intermediate values. So on the right here, you can see we have a very basic set of coordinate frame transformations. We have like a pixel image coordinate system in one, and then we've got some sort of like a focal plane or detector coordinate system in 2A and 2B, and then we have a spacecraft coordinate system in 3. None of that is available via the CSM standard. It is literally just image coordinate, body coordinate, and that's for a very specific reason. So like I said, this came from terrestrial and government intelligence and such. And so there's a lot of classified sensors in that world. And so what happens is they use a replacement sensor model where you effectively, instead of doing a full photogrametric, geometric mathematical representation of the sensor, you go to a purely mathematical representation, such as like a rational polynomial model, where you have just a single simple equation or something with some sort of non-physical coefficients in it that define the model. And so because we don't expose any of these intermediate parts in the CSM standard, you can have those replacement sensor models and all sorts of different models. The internals of your model are really up to you. So this has its advantages and disadvantages, which we'll talk about a little bit later. Similarly, we don't know the position of the observed body relative to other things. So the most common example is the sun. We can get things such as illumination directions, but we cannot get distance to illuminating objects necessarily. So if we're doing some sort of like image calibration, we want to be able to get the distance to the sun from a given ground point so that we know how to put the solar distance into the calibration equations. We unfortunately can't do that with just the CSM standard. We're actually kind of currently investigating different ways that we can try to add extra information to do that sort of stuff. And then something that used to be true, but isn't anymore, is different ellipsoids and different bodies. So this was very much literally hard-coded to WGS84 terrestrial everything. So when you did, you can do approximate intersections with just an ellipsoid. It was literally hard-coded to intersect WGS84 ellipsoid. So something that we've actually worked with the Community Sensor Model Working Group is getting the standard adjusted and modified to work with all of the different situations we have in Planetary. So it now does, I believe it was added in 3.0.3, that you can have a settable ellipsoid so that if you have different target bodies, you can do different things. But again, that's just for approximate things. You still need to be doing your own surface modeling and such. Okay, so that is kind of the API and the standard. And now from here, I'm going to be talking about sort of the two different worlds. You have the implementations of the API, which I'll talk about here first. And then you have the sets or the exploiters of the API, which I'll talk about later. So our primary implementation of the CSM API is called USGS CSM. I'm sorry if any other USGS Science Center ever wants to make one of these things. We can argue about names then, but that's what we've decided to call it. So this is, like I said, a plugin library. So it's got a plugin and a handful of models in it. Ours has 3 models. We have a generic line scan model that is actually adapted from a line scan model we had for socket set, but that we've basically worked with BAE to get open source, and then we've evolved that further to support more things such as variable rate line scan cameras, things such as we implemented some faster algorithms here and there. It's evolved pretty significantly. We have a generic framing sensor, and then we also have a mini RF monostatic SAR sensor in there right now. Those two we wrote from scratch. They are based on the ISIS implementations, but adapted to the CSM API and modified slightly. So we're kind of hoping for this to be a very generic library that, as long as you can get all of your ISD data and stuff properly set up, it can do the basic photogrammetric processes that we need to make this work. So that is USGS CSM. Here's just a quick kind of breakdown of what we currently support for sensors. The most robust support is right now for high-rise CTX and LRO NAC. Those are just the most tested, but we've kind of validated all these other sensors. We just haven't done the big testing and real data and production. That's really where we're at right now, is transitioning from, this has been in the software development world for the last 4 years or so, and now we're starting to move more towards the production world and really getting those reps in that you need to get the software matured and stable. So I said that USGS CSM is generic, and whenever you've got such a like heterogeneous set of data as we do in planetary science and planetary remote sensing data, you're going to have some sort of kind of homogenization layer. And for us, that is a software package called ALE. We call it Abstraction Library for Ephemerides. I've heard it a million different ways. I'm sorry if I pronounced that wrong to all the astronomers out there. But what this does is it takes primarily your SPICE data and your image labels, but it can also work with other data sets. So you can have ISIS cubes, you can have PDS labels or ISIS labels, or we're going to add support for PS4 labels, and all these different things. And it homogenizes that information into an ISD that USGS CSM, and actually now we're transitioning ISIS to using this, can make a sensor model from. So this is our layer that homogenizes our data into these generic formats. So this is really where the sensor-specific support lives. On the USGS CSM side, it really just sees binning or TDI or focal lengths. It doesn't see, for example, the messenger temperature dependent focal length formulas. That all lives in AL. Okay, so that is USGS CSM, our sensor model implementation library, really. That is kind of below the API is how I like to think about it. So let's talk about some of our support for above the API. And I'm going to talk right now about ISIS. I'm going to give a demo of using this CSM in ISIS, but I really want to stress the real value of CSM is the standards part of it. So if you're working with the CSM API, either writing your own plugin library or writing a sensor exploitation tool, you can share with anyone else who's also using that. So there's a list at the end of this of some other programs that use the CSM standard and support the CSM API. The great thing is that I can take USGS CSM and work with it in ISIS, and then I can go to Socket GXP and work with the exact same library, the exact same models in Socket GXP. So you can take your models with you wherever you go as long as they support the standard. And then the same thing is true the other way. So, at the USGS Astrobiology Science Center, it's called ASC or whatever, we do a lot of sensor model work, but there's other people who do sensor model work. And with the CSM standard, if you write your sensor model to support the standard, or you add a wrapper to your sensor model to support the standard, then we can just plug that right into all these existing tools. So it really allows us to share our software and share our data in a much more robust way than a lot of current tools do. So again, I'm talking about ISIS, but really the value here is the standards and the interoperability that we get from using them. So over the last 2 years, we've put a lot of work into getting CSM supported in ISIS. And this is kind of a quick rundown of where that's gotten to. So first of all, it is a plugin architecture, and we use a very standard plugin scheme where we have a directory that's specified in your preferences file. And then all of the plugin libraries in that directory are loaded at runtime and available in anything that uses this. On the ISIS API side, we have effectively wrapped an ISIS camera model around a CSM model. And that's because for the most part, the CSM model supports a subset of what the ISIS model supports. I'd say it's roughly 90–95% of the functionality. The primary gap is 1, solar things, and 2, relation to J2000. So computing universal right ascension declination and such values. Like I said, with CSM, it's really just what you're observing and your sensor. You don't have the ability to get information about what's outside of that. So something we're exploring is how to add that information to ISIS and other sets in a transportable way. Similar to in ISIS, how you have a SPICE init application to associate all the information your camera models in ISIS need, we have a CSM init application that just takes our model state string and just slaps it on the cube. And then from there on out, that cube is living in CSM world. You can flip-flop between them with the same images if you want, it all works. But we really recommend that you pick your model at the beginning and you only stick with one model. You can have a mixture of CSM and ISIS cameras and models. So for example, if we're working with, let's say we're working with some LROC data, we could use a CSM LROC NAC model. We could use an ISIS lunar orbiter model and a CSM, Apollometric model. Those will all play together nicely, but within each data set, you really want to stick with one thing. You don't want to mix ISIS LRO NAC and CSM LRO NAC models. You're just going to get yourself mixed up. And finally, one of the big things that we really wanted to emphasize is that for CSM, once you have this model state, that is everything you need for your sensor model. So there's very, very little information you need in your image labels compared to ISIS camera models. And you can start with literally just raw, you can start with a raw binary IMG ingested into ISIS. And as long as you have an ISD and a plugin library for that, you're good to go. So someone always jokes about, well, I should be able to take my DSLR camera, take a picture and load that into ISIS. Before that wasn't really possible. But now if you have a CSM plugin library for that DSLR camera, and you have an ISD for your image, and you have your IMG from your DSLR, you can pull that into ISIS and work with it. So it's added a lot of flexibility there. Okay, getting even more recent, the big thing we did this last year is adding the support for bundle adjustment with CSM and ISIS. And this is just a very quick rundown of the workflow. If you're not familiar with bundle adjustment or photogrammetric bundle adjustment, as it's more commonly called, this is effectively a giant optimization problem. So we have all these images, they all slightly disagree with each other. We then make a bunch of observations. So we say, hey, this crater shows up in these 8 images, or you can see this specific ridge in these different images, or in rover images, you can see here's the horizon in this image. You take all these observations about your data set and you put it into a big mathematical model, and it basically gives you an optimized solution for your sensor parameters and for your target and ground parameters. And what this does is it basically makes all of your data agree with each other. It's not going to make all of your data correct. That is 100% on you as a user to do it correctly, but it will make all of your data agree with each other. And if you do it correctly, then it will make your data quote unquote correct. So just really quick running through this. You're going to start out, you're going to associate your CSM models with your images with CSM in it. You're then going to build your control network just as you normally would in ISIS. A big word of warning here for those of you familiar with ISIS and serial numbers, because we do not require any label information for the CSM models, your serial number will be different for the same image with a CSM model and an ISIS model. If you want to take an ISIS control network and work with it in CSM world, there are ways to do that, but it's a little tricky. And I'm not going to put any information here. If you want to do that, please reach out to me. I'm more than welcome to help you with that. Next, so we've built our control network. We've gone through, I'd say 90% of the work probably here is exactly the same. Now you need to figure out what you want to solve for. So this is a big departure point for ISIS and CSM is the model parameters. So in ISIS, our model parameters are things like spacecraft position, spacecraft acceleration, spacecraft sensor pointing angular accelerations, things like the target body rotation. Very physical, standardized across all ISIS sensors. CSM is kind of the opposite end of the spectrum, where every single model can have a different set of parameters. It is up to whoever implements that plugin library to decide what parameters they would like to expose. And it's up to them to really document what those are. So please, 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 if you write a plugin model, please document your parameters so your users know what they are. What you get exposed via the CSM API is literally a name, units, and a type. And we'll look at that later. So you need to know your models and you need to know your data set so that you can figure out what you want to solve for. Finally, you're going to run Jigsaw, and you can either do the standard ISIS process of running, cam to map and then mosaicing all your stuff and building a nice, beautiful mosaic. Or the new thing is you can then dump your model states with the blob dump application. And then now, like I said, as long as you have that plugin library and that model state, you're good to use your adjusted models anywhere that the CSM standard is supported. That's like the real power here is you can use the robust control processing tools in ISIS to get good model states. And then you can feed that into other programs that use them to make excellent things such as stereo DEMs. So I'm going to pause here for just a second. Are there any questions before I go into a demo on this? Yeah.
There were a few questions in chat from Michael. I don't know if he still wants to bring those up.
I see these.
Hey, hey, yeah, so the ISD confuses me a little bit and the relationship between AL and ISD.
Yeah, so
if there is any.
Yes, so AL is primarily It's actually two packages, really. There's a Python side and a C++ side. The Python side is really what I've been talking about here. That is an ISD creator, but that is an ISD for USGS CSM. So there's a previous comment from you about how is it standardized? It's not very well standardized. This is part of the standard that I'm not super happy with. For a lot of the government, DoD, NGA stuff, they use NIDIF headers, which is a standardized format, but we don't use those really in Planetary. And so what we've done is we've basically created a JSON formatted string that we use for that. But it is specific to USGS CSM, and there's ways with the API that you can work with it. So it's not that it is so unstandardized that you can't work with it. It's just that when you're writing a set, you have to do a little bit extra work to make sure you try all the different possibilities for the ISD. There's like a hierarchy of like, try this one, try this one, try this one.
So I think this is just a confusion of terminology or what I confused. I thought you said ISD is standardized, and I think what you meant is that the way to create an ISD is standardized, but the content of it is circumstantial metadata, right? Like these temperature dependent focal lengths and things like that.
Yes, exactly.
Oh, okay.
I would say that is correct. That is the most confusing part of the standard is like the plugins and the ISDs.
Yeah. All right. I think I'm good. Thanks.
You also had a question about the locus. I can talk about that. It's not a vector or anything. It is very much just a set. It is an abstract set in space. So like I can back up for just a second here.
Yeah,
you can see
as a set is an abstract, what does it describe in nature?
Yeah, so in nature, it describes a set of points. Basically, it's like it is the set of points in nature which that image coordinate could have observed. So for a pinhole camera, that's basically a straight line from your whatever your detector is through the pinhole out into whatever you're imaging.
Oh, then I don't understand the graphic, because true imaging locus seems to be just aligned at the arrow, but not pointing to anything. That's why I was confused.
Yeah, so what's happening here is that you can see there's some atmospheric like diffraction, I believe is the term going on, because this is Earth observing primarily. And so the true image locus is not a straight line vector, it's a curved line in that situation. And so the way the standard works is that you can approximate it with an iterative process. It's a little complicated. I didn't really want to get into the details of it, but
yeah, but then is the locus the end of that curved line or the curved line itself?
It's the entire line, because if you think about it, you can have that line intersecting multiple points. So if, for example, there was a cliff right here, right where this word true imaging locus was, you could intersect the top of that cliff and the bottom of the cliff and then the actual ground. And it's up to the set to determine which of those three potential intersection points are true. This is the occlusion problem. Excuse me. And then you also have other situations, like I said, with SAR, where you have a ring of constant distance effectively. And so that anywhere on that ring that it intersects the body is where you could have gotten your response back. And so the locus can get quite complicated, but you can have it be just a straight line. And that's one of the parts of this that is valuable, is that it is generic enough to support all of these different types of observations with different types of sensors.
Is it wrong to imagine the locus as the path the photons took to get into the camera?
For an optical sensor, that's basically correct.
Okay.
For a radar sensor, that's not necessarily true.
Yeah.
For an active sensor, it's even more complicated. So yeah, that is the basic interpretation.
Okay, thanks.
Okay, I'm gonna roll right along into the demo. I see, I think I have a question. Yes, SAR is an active sensor, but I'm talking about an active optical sensor. We have some weird ones like that where you're doing slightly different things.
Well, yeah, I mentioned the backscattering of a LiDAR.
Exactly. If I can get out of PowerPoint. Okay, so I'm going to do a quick, not too quick, probably about 20-minute, 15-minute live demo here, just showing how you use all this with ISIS and giving you a little bit of a concrete understanding of everything I've talked about. So right now I'm set up with a Anaconda environment. I have ISIS 6.0 installed right now. The bundle adjust capability was added in 6.0. The CSM camera model capability, I believe, was added in 5.0 or 5.1. I can't remember which. So if you want to do the bundle adjustment, you need 6.0, the latest release. The other important part of the setup here is in my ISIS root, I have a CSM libs directory, and then it's versioned for the CSM standard. And then in here, I have my plugin library for USGS CSM. And what I've actually done is just made a symlink. So I have a separate Anaconda environment that I've installed USGS CSM into, and then I just need to symlink that library into this directory. There's other directories that I can put it in. You can see it all in your ISIS preference file under the plugin section. So you can see here is the ISIS root. Sorry, here is the ISIS root libs, CSM libs. You can also put it in your home directory. You can put it in your lib directory in your environment. You can also put another thing onto this keyword. It's totally user customizable. Okay, so that is the kind of tool setup. Let's talk about the data I'm be working with. So this is a CTX stereo pair from the North Syrtis region, I guess. This was a potential landing site for Mars 2020. Trent Hare got this data set together, and I'm just piggybacking off him and the Apple group's excellent work that I'll mention a little bit more later. So I have, oops, I need to delete some stuff because I've got some old stuff hanging around. Okay, here's what I've got. I have some ISDs. So again, the ISDs are both kind of standardized format, but specific to your plugin library. So these are USGS CSM ISDs. If you look at them, they are JSON formatted files. They have stuff such as times, angles, quaternions, all that good stuff. I also have some.
So where did you get them from?
I generated these with Ale in the past.
I see. Okay, thanks.
I have some control networks. These were made using the data that we'll get to. I just kind of skipped over that part for time's sake. I just used a standard auto seed, which just places ground points and the overlap between the images. And then I did a point reg to get a registration on them. And then I cleaned it up just a little bit from there. I have my original ISIS cubes. So you can generate ISDs from a lot of different things. For CTX, you can have an ISIS cube that has been spice knitted, an ISIS cube that has been bundle adjusted, an ISIS cube with just the ISIS data area, an ISIS cube with the PDS kernel release. You can have a PDS image with the kernel release. I think that's it. But it can take all those different data inputs and homogenize it down into this ISD. So in this case, I used a spice knitted cube to generate my ISD. And if we look at them.
I was just puzzled that you said, yes, you can a spice init cube, but also a bundle adjusted cube. So format wise, you can take them, but the result will be different, right?
Yes, totally.
Okay. Okay, and just to make sure that I get
any differences in your input data will be reflected in that ISD.
Right. Okay. No, I was just wondering if homogenization means here that it's somewhere forgetting what the bundle adjustment was and goes back to some kind of default state, or
it is just homogenizing the format.
Right. Okay. Gotcha. Thanks.
So this is very standard ISIS cube. We have an instrument group, we have an archive group, we have some kernels, we have band bin information, we've got a bunch of blobs on here, we've got some radiometry from some flat field correction, all that stuff. What I've done is I've dumped these to PNG and then re-ingested them. And in my raw cubes directory here, I have the exact same cube with the absolute minimum label information. We have some information about our pixels. We have the most basic information about our band bin, which is actually not correct in this case. We have a description of our label object, and then we have a tiny amount of processing history. For ISIS camera models, you would be dead in the water here. But one of the excellent things, like I said, about CSM is that as long as you have that ISD and the plugin library, you're good to go. You don't need additional label information. You don't need some specialized ingestion program. You can homogenize all at that one layer.
Maybe I missed it earlier, but like how much work is it? Is it just a command line tool, like given the CTX image ID, get me my ISD JSON file?
Yeah, so we have a single interface. It's a Python module that you load. You do need to either specify where you have your PDS Spice kernel archives located, or you need to do like 2 calls to get the ISIS data area kernels location. And then you call al load, and it basically just takes all that data and spits out an ISD, either in a Python dictionary or in a string. And then you write that to a file. It's pretty straightforward. So like the script that was used to generate these is like 10 lines. Okay, so let's get to some actual processing here. The first thing I'm going to do is I'm going to run CSM init. I'm going to give it my, oops, sorry, actually, the first thing I'm going to do is I'm going to copy these. This is just a, data processing best practices thing that I was always taught is like, whenever you modify something in place, you should copy it over so you don't modify it in place unless you really don't want to build up the extra stuff. So I'm going to give a cube here. So this is the cube I want to attach my CSM model to. I'm going to give it a ISD. And then, like I said, CSM doesn't do surface modeling, so we need to add a surface model. I'm going to use a MOLA cube here. And then the other thing is that CSM doesn't know what your target is, because it was always assumed that it was Earth, and now suddenly it's not. And so the one additional piece of information that you may or may not need is to tell it that, hey, we're looking at Mars. So I'm going to run that. Now, if we look at our cube, it's got a bunch of extra information on here. So we've got a little bit of information about our instrument. We have our service model here. And then we have some information about our CSM model. So we have a platform ID, which is basically your spacecraft, an instrument ID, which is your sensor, a reference time for the image, and then here are all of my parameters, which we'll come back to later. So just remember that this is all here now.
Jesse, sorry for the noob question. Does this shape model mentioning in the label here now mean that your calculation results will be bound to this molar map, like in the old-fashioned way of co-registering images?
It's the same way as an ISIS camera model. So if we do an ISIS, we don't really use the locus externally. Inside the camera model, we use the locus, obviously, but the camera model API basically says, take an image point, give me a ground point. Take a ground point, give me an image point. And when it does the calculations, it will be using MOLA. It does also compute that locus. In ISIS, we have to reduce that to a single look vector, though, because of how the ISIS camera API works. But if you're working with something else in the CSM API, so for example, we wrote a separate bundle adjustment on just the CSM API. In that case, we worked 100% with look vectors to create our a priori ground points. Does that answer your question?
Well, I guess for this height calculations, I understand, but I'm feeling, not sure if I'm correct, that this doesn't yet mean that your results are bound to a molar map. You know, like when you want the same point in your CTX images to be pointing to the same map on the molar map. You know what I mean?
Yes, no, correct. I am not registered to MOLA. I'm just using MOLA as a topography.
All right, gotcha. Thanks. That's what I wanted to understand. Yeah.
Okay, and the last thing I want to point out is the CSM state. So this is our model state that has been serialized to a string and is now appended to the end of my image label. We'll come back to that later. Okay, I need to do this for my other cube real quick. Okay, that one's all good to go now. Let me pull up my cheat sheet real quick. Okay, so let's do some basic processing. One of the first things you're going to do with any control processing is generate your image footprints. So let's do that. Using the footprint init application, I'm going to give it a line increment of 10 pixels. So this is going to basically go across the image every 10 lines and 100 samples. It will compute a ground point, and then it's going to take all of those ground points and figure out what the footprint is. I've made my line increment a little smaller here because this is line scan data, so I want a little bit more precision in the line direction. I'm not as concerned about the sample direction. Do the same thing there. This will take just a second to run. And then what I'm going to do next is I'm going to pull these up in QMOS. You could also pull them up in like QGIS if you're more familiar with that, or ArcMap. And we'll be able to see the computed footprints. Again, this is all using that CSM model on the back end. Yep, so here we go. We can see I've got my two images, my B17, B18 image. They're a stereo pair, so they have this very nice overlap relationship. You can even see that there's slight variations along the edges from both the motion of the sensor and the surface topography. The next thing I'm going to show you guys here is my control network, just to show everybody what it looks like. This is what our ground point spread looks like. You can see there's a very regular grid to this. That's from AutoSeed. AutoSeed lays down these very nice grids in object space. I've gone then in and registered these points. So I've registered the B18 image to the B17 image effectively, and trimmed out anything that did not have sufficient correlation for my concerns here. Luckily, these two images are like beautiful. They may have been pre-processed through some other things, but the nice part is that AIL has basically homogenized all that out. It just said, whatever your cubes were in, whatever has been done to them, I'm just going to take that information and just slurp it into this new format so I can pull it into CSM, or at least into USGS CSM.
Jesse, all what you just said in the last 2 minutes, could that be another talk?
Probably, but I'm not familiar enough with this to do that. Go talk to, I believe this was done in the Mars 2020 process. So okay. talk to Robin or Trent or some of the JPL folks about those processes. And again, the real takeaway here is not the specifics about USGS CSM. It's like any CSM plugin library can be used in this way. So if someone wants to go write a CSM plugin library for whatever sense that they like, we can just plug it right into ISIS and a bunch of other tools. Okay, so next on my list, we're going to pull up QNet and look at our network a little bit more detailed. Okay, so let's just like pick a point here. This thing always gets tiny, I don't know why. So if you're not familiar with QNet, what we're looking at here is the common observations of a ground point in our two images. So on the left here, we have the B17, on the right, we have the B18 image. They look really good. That's because the A prior here is very good. But I can turn on this blink tool and it's you can see there's a slight breathing that's happening. And that's partially from the stereo parallax. And it's also partially from just, uncertainties and errors in the pointing. So they don't 100% agree. So the nice thing is I can turn on this geom, and this is using the CSM model on the back end to basically compute an affine transformation between our two images so that it takes out that difference. And this is what really makes point reg and QNet and stuff work so well, is that we're able to take out the distortions from the different observations and get a much closer match. So you can see that this is way better lining up now. It's just slight tone differences and such, and slight noise differences, and also some illumination differences.
Yeah, that's really cool. Although I'm trying to understand, like, this like sounds like all very similar to georegistration. Orthoprojection. So is that effectively what it's doing? But it can't do orthoprojection just that line.
Yeah, it's effectively. So instead of going from image space to ground space, what is happening is it's going from image space to ground space back to image space. So it's going from B18 to the ground, and then it's taking that ground and going back to B17. And then it uses those relationships from 17 to 18 to compute the affine transformation. And this is all standard ISIS stuff that's been around for years, but it's using that CSM model on the back end now.
Okay, got it.
Okay, we're gonna keep moving. We got some more stuff to get through. Okay, let's get into the actual jigsaw run. So first of all, I'm gonna potentially be modifying these cubes. So best practices, let's copy them somewhere else. And then because ISIS loves list files, I'm gonna make 2 list files. I'm gonna make my images list file. And I'm also gonna make a held list file. So because I have basically registered the B18 image to the B17 image, I'm gonna hold the B17 image fixed. I don't want it to be adjusted. What I wanna do is I wanna adjust B18 to better match B17. If I'm worried about global control and global alignment, I will go bother David Mayer, who I see is in the chat, about some of his PC align work and ASP of once I have my stereo pair nicely aligned together, I can then register that and move it to align with the global data set. So in this situation, I'm gonna hold this one fixed. Okay, now I'm going to copy over a gigantic jigsaw command because jigsaw commands are always giant. But I'm going to explain this. So jigsaw is our bundle adjustment tool in ISIS. This is what makes everything agree. And let's just kind of real quick run through what these different arguments are. So from list, this is the list of images I'm adjusting. Held list, this is the images that I want to hold fixed. These are the 2 images, the 2 lists I just made. I have a control network as my input. I have a control network as my output, because one of the things Jigsaw will, in addition to the image, it will also adjust your control network and your ground points. I want to solve for radius. So you can solve for latitude and longitude, or you can solve for latitude, longitude, and radius, or you can even solve for body fixed X, Y, and Z. I'm going to turn error propagation on because, errors, uncertainties, one of the big things of CSM is getting that error propagation so that your input errors can be translated to your output errors. For my point data, I'm going to just give it some somewhat arbitrary uncertainties. So I'm going to give it a 10-meter uncertainties in the latitude and longitude direction and a 100-meter uncertainty in the radius direction. And then here is the big new CSM thing. So in ISIS solutions, you would do like cam solve or SP solve position or cam solve angles. In CSM, you can either specify sets, types, or an explicit list of parameters. In this case, I'm going to give it an explicit list of parameters, and this is parameters defined by the USGS CSM generic line scan model. So I have omega bias, omega rate, and omega acceleration. So those are angular offsets. The bias is a constant offset, the rate is a linear offset, and the acceleration is a quadratic offset. And the angles are omega phi kappa, which are basically analogous to roll pitch yaw. So omega is effectively our downtrack angle in this situation. And I'm going to solve for a quadratic offset to that. So it runs. We got nice and resolved. The big thing you always look at is your sigma naught. This is effectively a measurement of the remaining error in the network. We've got a 0.6, which is pretty good. It's not amazing. And that's due to some things about how I'm doing the solution. If this was really for true project work, I would do a lot more work and I wouldn't hold an image fixed. I'd just highly constrain it. And there's a lot there that I'm not going to go into, but we got a nice solution here. I can look at my output files. Let's look at the TXT file as a human readable file for us. We can see here's my residual percentiles. So this is effectively for all the ground points in the network. If you back project them in the two images, what is the residual and image space? Sorry, if you back projected the image, what is the residual between the back projected and measured location? This is not great. This is where we can do a lot of improving if we had a more sophisticated control network generation technique, but I didn't really have time to explain that here. And that's a whole other person's job, so I don't feel comfortable explaining it. But I really want to show you here is this, our image exterior orientation. So these are the parameters, our omega bias, omega rate, and omega acceleration parameters. You can see for B17, our corrections are very small. We don't actually hold it truly fixed. We just incredibly highly weight them so they don't shift very much. But we can see here for B18, they have shifted quite significantly. The other thing you'll notice is that it is in meters. That has to do with some of the stuff on the back end we're doing in USGS CSM, where we want our image parameters to be roughly the same as our ground point parameters. So if you adjust an image parameter by 1, we want that to be about the same as adjusting your ground point by 1 meter. So that's why this is in meters, and that's why we're not actually correcting like 26 degrees or 26 radians here. We're correcting an angle that results in roughly a 26 or 27 meter difference on the ground. That's what these are. And as expected, you can see our constant offset is large, our linear offset is slightly smaller, and then our quadratic is slightly smaller still. All looks good. We have uncertainty values. We started pretty high. Uncertainty values ended up pretty low. If you're familiar with ISIS bundle adjustments, you'll notice we didn't input these values. That's another big difference is in ISIS, you have to put these into Jigsaw. In CSM, they're a part of the model. The model retains its uncertainties. So these uncertainties are now actually stored in the model and will follow along with it for future use. Real quick then, I'm just going to show like one more thing. So that was a good solution, but it's not perfect. So let's throw another angle in the mix. I'm going to throw the phi angle, which is our cross-track angle, effectively into our solution now. So we're solving for omega bias rate and acceleration and phi bias rate and acceleration now. Everything else exactly the same. I'm just going to put it out to some slightly different files. We can see our sigma naught is slightly lower. You're shooting for a sigma naught in Jigsaw of about 0.5. 0.5 is 100% perfect. In other bundle adjustment programs, your sigma naught might be 1, but in ISIS, how we do the computation, it ends up being 0.5 is perfect. So we got, by adding that extra angle in there, we got a slightly better solution. And if we look, we can see in our image parameters section that, yeah, we do have slight corrections to our phi, but you can see that they're slightly smaller than our omega. So this tells me that the majority of the error between these two images is going to be in the down track direction, is not in the cross track direction, which is what we expect. Usually the majority of the error we see in these things is, you know, slight timing offsets and stuff. The pointing values, particularly for a lot of these orbital emissions, tend to be very well behaved. So that is a really quick rundown on bundle adjustment with the CSM stuff. The last thing I'm going to show you is the model state itself. So like I said, we have the model states associated with the cubes. And the real value of CSM is that once you have that model state and the plugin library, you can take it somewhere else. So you can use the blob dump program. And now I have taken that model state and written it out to this. It's really a binary file with a PVL header file that has that updated model state into it. If I look in this file, if I can get less to work properly. Did I? Oh, I keep misspelling. Here we go. So, oh, oops, my bad, sorry. I forgot to turn on update. There we go. So now, because I've turned the update on, it has written that out to my cube, the updated state. I can dump that out. And here you can see in our current parameter value vector, all of those corrections that we had to our model parameters are now in this model. So if I create a new model from this model state, it'll have all of my adjusted values in it. And I don't have to pass around a huge cube. I can literally pass around this file right here that is 25K. So you could even potentially stream this over like the wire, which is awesome. Okay. That is the end of the demo. I'm sorry, I'm a little over. If you want to play with this data, it's at this location along with a couple example data sets. They are in different states of how good they are right now. So user beware, like I said, we're really getting into production testing right now. But if you would like to play with this, that's available there. All the software I use that's available on Conda right now. Let me know if you have trouble installing anything. So there's other tools that support CSM. There are things such as Socket GXP, AIM Stereo Pipeline, Envy, Erdos, Awesome, ArcGIS, all of them have hooks for CSM. So you could take USGS CSM and plug it right into those things. You could take a CSM library from someone else and plug it right into those things. At Astrogeology, we've also developed some other tools. We have Swig CSM, which is a Swig Python wrapper that gives you direct access to the CSM API in Python. We also have Knoten, which is a little bit of extra Python on top of that to make things such as model generation easier. And we're hoping to kind of expand that to provide more robust support for things such as surface model intersections, so that if you really want to tinker directly with the camera models, you can. This is kind of a quick breakdown of where we're going to go. I don't really have time to go into it, but I do want to give a thank you to Trent Hare and Rainey Kirk for really getting this ball rolling about 5 years ago. I'm amazed at where it has gotten to. The ASC development team has been awesome. This is years and years of work, and I'm super happy with how it's gotten there. The ASC APL folks, I know David, I saw you're on here. I appreciate all the work you guys have done in testing and just running this through the paces. NASA Ames Mapmakers and LROC team have been great external collaborators on this work, and the CSM working group has been super great to work with. They've been super open and really wanting to know how can we make this better for Planetary. And then I'd also like to thank NASA for funding all of this, and Chase and Open Planetary for having me today. So